Can I get started? Wow, that was really loud. Or at least, wow, we got that echo. Okay, yes, hello. Yes, this is the last workshop. I will never have to make slides again for this project. At least as of now.
And I can click since you're talking.
Well, but you're gonna talk like right now.
Okay, fine.
Anyway, congrats. Thank you for being here. It's the last one. Thank you for being dedicated members. Okay, let's get started.
Hell yeah. So, part one of this workshop will be about Hamming windows, which is a fun way of eliminating something called spectral leakage in your FFT. So, suppose for a moment that you're a DAV student, right? And you're working on completing your digital audio visualizer capstone, like this DAV student that is probably working on a capstone about digital audio visualizing. And so also suppose for a moment that you want to learn more about the fast Fourier transform signals. How would you go about doing this? Well, you would show up to this workshop where we teach you about fast Fourier transform signals. And among that, we will teach you about this concept called spectral leakage, which is basically, if you see here, we have an example of a graph, right? This graph of an impulse plot that you might have seen from like 102 or something. And what you expect is that when you compute the FFT of a signal, you should get this very clean impulse plot that has spikes only at the constituent frequencies and zero everywhere else. However, since we're working in the discrete domain and not the continuous domain, our data is obviously less accurate, less precise overall, and as a result, what we actually get is something that looks more like this. It's a giant spike and then just some ripples in either direction. And it looks a little weird. So the problem is that our computer can't really compute the FFT of an infinite number of points. So the actual, this is what the Fourier transform mathematically requires, right? You take the periodic signal and you compute frequencies out of it. But what the computer does, since it's a discrete signal that's sampled like a certain number of samples, it takes that discrete signal, it makes it periodic just by repeating it over and over, and then it tries to compute the Fourier transform of that using the FFT algorithm. So the actual sine wave that's being processed looks a little bit like this. You take this sample that's cut off at 16 samples or how many ever you have. It repeats it internally, and then it computes the FFT, and what it gets is actually multiple different potential frequencies, right? You have the original frequency, which is down here, and you have this much faster frequency that contributes to these little at the edges of your periodicization, basically. So this sort of extra frequency that's being detected in this signal is called spectral leakage. If we want to get a clearer idea of what frequencies our signal actually has, we have to eliminate the spectral leakage somehow. So this is the equation for the window that we use to compute, basically the window that we look at in our signal. It's not really important. This is some random other stuff that we found. You can examine it at your own leisure.
Yes, I found it. They're real.
How do you pronounce it?
Dealer's choice.
Fair.
Alright. But yeah, this isn't that important. It's just good to keep in mind that the windows that we choose for our signals have some sort of mathematical basis. But basically what the idea is in order to eliminate spectral leakage, the goal is to eliminate these high frequency components, right? And so I'm going to switch to this with a whiteboard real quick to demonstrate. Is it visible? Hell yeah, first DAV whiteboard lecture.
Ew.
But anyway.
You are in frame.
So what we have is a signal with, this is, literally world's shittiest marker. Alright, we have a signal. Okay, this is better. We cut it off at some point, and then we repeat it. So keep in mind the periodicization is not actually something we do. It's just something that internally is part of the math for the Fourier transform or for the FFT. So what we have is these high frequency components, as you saw in the diagram, and the solution to this is actually you take this window that we're looking at, and you find a way to sort of make the distance between these edges a little bit smaller, right? And the way to do that is just by attenuating the edges of this sample, the window. So instead of that, we kind of like, if you can just like if you can say that like this entire window is being compressed into this sort of space. So it's more like kind of, it's like a horrible drawing, but I will draw this better.
Is that what that multiplication is?
Yes.
Okay.
So it's like, basically you're taking this original window that looks like this, and you're compressing it down a little bit to fit in, basically so to where the edges of the window are attenuated. And as a result, now if you were to take this and repeat it periodically, it actually like connects, as you can see. Yeah. And this obviously looks like a much cleaner signal that we can easily compute the FFT of, and the bonus is you don't notice any absurdly high frequency components that are happening like you do in the original one. So the coefficients for actually multiplying the window are given by the Hamming window formula, which is given here. Basically, this W sub n is just like the coefficient for a given sample in your window. So as you can see, before the ideal sine wave that we would expect from like that we're like sampling, it's going to be a pure sine wave, and then the frequency plot is a perfect impulse. What happens when you compute just take a window of it, like 16 samples or whatever, you have these high frequency edges that are contributing to spectral leakage, these ripples over here. In reality, what we want is it to look more like this, where if you compute the Hamming window, it's compressing those edges down to where they can kind of more cleanly connect to each other, and there's no weird extra high frequency component. And as a result, we get a much cleaner frequency plot that is a little bit wider. The actual frequency computation is less precise, but that's the trade-off for eliminating these ripples on the sides. Does that make sense to everyone?
Yeah, just so.
Question?
I guess since we're dealing with like a discrete case, so instead of like having like these continuous lines, we're just gonna have like a histogram, right? So how do these, if you make your bin size big enough, do these ripples still show up?
If your bin size is even small enough?
Yeah.
Yes, because ultimately it depends on whether or not you're sampling fast enough to make these depending on how fast you're sampling, right? But the thing is, these edges will show up if the edges of your window are not attenuated enough to where this first sample and the last sample aren't necessarily connected, which is going to be the case most of the time because you can't really account for that. So I'm not sure if I'm answering your question correctly, but I think the intent with sort of making the bins smaller is not so much to actually eliminate this sort of spectral leakage, but more so just to improve the overall precision of our FFT, which still comes with some spectral leakage, but it doesn't necessarily eliminate all of it.
Also, just to add on, so the trade-off between spectral leakage and the width of this spike is that the more you try and compress the spectral leakage, the wider the point gets, to the point where it's too wide and you can't actually tell what frequency it is.
Okay.
So the Hamming theory is that he found the number that has the best trade-off between the two.
You went ham.
Yes, indeed.
Yeah, so this is a screenshot of an actual Hamming window, where you can see this is the original frequency spectrum. It has this little curvy edge that's the spectral leakage, and if you were to apply the Hamming window, it kind of compresses it down, as you saw on the board, and the result is the little curvy edges are gone, but it's a little bit wider overall. Does this make sense to everyone? Cool.
Okay, it's my turn. You want to push on? Yes. So here I am, previous publicity here, to talk about pretty colors, because I guess that's all I really do. If you want to go on to the next slide. So we're just going to cover gradients really quickly. They're actually a lot easier than you think. In fact, Craig and I made one on accident. you can take advantage of your positional data to create some really pretty colors. Notice how like they all blend pretty seamlessly together. So this gradient, for example, was created by taking 4 bits from the x position, 4 bits from the y position, and the blue is constant. So it's just varying in red and green. But if you want to use like smoother gradients, because you notice on the previous one, it looks a little chunky. That's because you're skipping or you're varying over a position. So it's not going to change in this certain range. So if you wanted it to change smoother or quicker, then you would use I guess the lower bits of your position to do that, so it would change more frequently. But as a result, you'd get this repeating pattern, which is what Prem and I made somehow. But yeah, it's a really, really easy way to make some good looking colors, so I thought we'd bring it up. The second topic is slightly more complicated. We're going to cover dithering. So the concept of dithering is that you can make new colors by changing 2 colors in the same spot really quickly. So if you were to mix I don't know, red and blue, for example, really fast, maybe you get something in the middle like a purple. And in this way, we can use the fact that we only are giving ourselves 8 bits for a VGA, and we can make more colors by employing some math. So our VGA roughly has a refresh rate of 60 frames per second. So if we, on alternating frames, switch the color in each pixel, then we can unlock some new colors. Yes. So the trick behind dithering on the FPGA is you will selectively add or subtract a set amount from each pixel, and so when you alternate, they will have that difference between them that will blend to create that new color. So I have an example here. You can see that the one on the right is obviously much smoother than the one on the left, which looks a lot like the gradient we had before. So this may actually fix your problem, oh, I want a smoother gradient, but I don't want it to overlap. This could be a way that you do that. And so the technique that we're going to go into today is called ordered dithering. But before that, are you following along so far? Is it all good? Okay. Yeah. So it might look scary, but it's not too bad. Essentially, all you do is you have this set matrix that you're going to, in this case, we're going to add to each pixel value every frame. And the key is that we switch this matrix every other frame so that we have that little difference in pixels, and then we have that new overlap. So, for example, let's say we're taking this little box, so we just add 0 to this color, 2 to this color, 3 to this color, and 1 to this color. On the next frame, we switch it, so we add 3 to this one, 1, 0, 2. And so you see oh, this one may have a 3 pixel difference. This one only has 1, this one has 3, this one has 1. So you get that kind of color variation with that. You might be wondering, well, that seems kind of lame. Is that the only way I can change colors? No, there are multiple variants of this, and really it's you experiment to see what looks the best for you. So this would create a crisscross effect, as you see here, and then when these 2 frames overlap is when you get that one. So you just have to kind of think of these 2 just being stacked on each other, and that's what you would see on your VGA. A couple more things. I see you have a question. Some experiments that were not done by Prem or I found that if you use one of these matrices on one frame, but then in the same frame you use the other one, if you use this one on red and blue, but in the same frame you use this one on green, and then you switch it for the next frame, it becomes smoother for reasons unknown. Because the whole point of dithering is that you might get that flashing effect, but it's supposed to blend together. Yeah, what was it?
So when you alternate these 2 on top of each other super fast, would it look like a uniform thing? Because I guess you were stacking green and purple on top of each other. I'm not seeing why it would look different.
Oh, yeah, it basically, if you remember how you can get your LED to flash so fast on your FPGA that it kind of doles out.
Yeah.
The whole trick with dithering is that we are using this speed to kind of just mash these colors together. So, color theory. Maybe you would make a light blue, I'm guessing is what these guys would make. I'm sorry, my color theory is
So you just see a giant square that's just blue in the color.
I'm not sure if it would be uniformly, but it would like have like whatever effect you want, I guess. So if you have like different colors here or whatever, but honestly I think these are the same. So yeah, it would just be a uniform thing. Okay, so just to give an example of dithering in the real world, old game consoles such as Nintendo 64 use this to make their games look smoother. Now I'm aware that you're looking at this on a screen, and this is a screenshot of a screen. So the compression is already going to be awful, but if you look really hard, there's a stronger border in the sky here, but here it's a lot more mixed in. So this is just like a technique that's been used since the dawn of gaming, basically. So, yeah. Oh, it's the meme break. Hello. You're just in time. Oh, I didn't mean that. I didn't mean that. Okay. Enjoy these memes that I found. My personal favorite is this one because I'm not a physics enjoyer. But yes.
Alright.
Okay.
Does anybody have any questions?
Okay, let's continue then.
We can just continue. It's been 17 minutes, they don't need a break.
Okay, yes. Well, maybe these slides were made earlier this week, maybe they weren't, but we're
Anyway.
going into our filtering. Suppose you are yet another DAV student, but you're really interested in music. And what I mean by that, and what we will demonstrate shortly, is music mixing programs have something called channel EQ, where you can raise and lower the frequency balance of a signal, like your voice, an instrument, or whatever, at will. So we will talk about that for a little bit.
So basically, like, what we're going to be talking about here is the concept of time domain filtering, which is where you apply some sort of filter to a signal in the time domain through convolution usually. And there's a lot of reasons why we do this. For example, if you want to eliminate certain frequencies from your final frequency distribution, if you want to boost certain frequencies, like for example, bass boosting is an example of a filter. Basically, if you were trying to do something that would affect how the frequency distribution of your audio looks, you would apply a filter in the time domain. There are reasons why we do it in the time domain rather than the frequency domain. The main one being that if you do it in the frequency domain, you have to wait till your frequencies are calculated before you can apply your filter. And usually the computation of frequencies from your time domain signal is the bottleneck, so you want to apply the filters first. And the other thing is, if you apply the filter first, you can do it on the entire sampled signal as each time sample comes in, rather than having to take in a sample, wait for the FFT to finish computing, and then compute the entire filter on that frequency domain.
Yeah. Just gonna add on to that,
frequency
especially
distribution.
for music purposes, that trail makes bad noise. So extra reason why you want to do it in time domain.
Yeah. So the only downside, of course, is that if you are doing something as simple as a multiplication in the frequency domain, this is a convolution in the time domain. But for the most parts, this is like fast enough to where it outweighs all the drawbacks of frequency domain filtering. But yeah.
Okay, so this segment, I'm sure you guys already know about basic filters, but we didn't want to make slides for this, so we will demo it through my music mixing program. As a wise man said, we don't have to make slides if you do a live demo. Okay, let's see if I can pull it up. Okay, hello. It's Logic Pro. That actually rhymed. So I should have mirrored this because now I have to look at this the whole time, and also now I have to like.
What
turn
if you
on
mirror
my-
it now?
Well, but I'm too lazy to do that.
Okay.
Okay, so let's click on this one, and I'm gonna click on this guy. This is the channel EQ that we were talking about. You have a whole range of filters that you can use here. But most of these are mathematically complicated, so we're just really going to be demonstrating the two on the edge here. So we have a low pass filter here and a high pass filter, and if you combine them, you get a band pass, I suppose.
Does everyone know what low pass and high pass filters are?
Okay, great. So we're really
Should we
just
explain
here
for the
to-
recording? You should probably
yes, we
explain.
should.
Okay. So for those of you in the recording who may not know what low pass and high pass and band pass filters are, basically a low pass filter lets low frequencies pass through and blocks out or like zeroes out higher frequencies. So for example, something like if you have a signal that is if you want a bass boost, for example, what you're going to want to do is it's like kind of like a low pass filter, except you actually increase the amplitude of your lower frequencies and sort of zero out your higher frequencies to improve the bass in your signal. The high pass filter is the exact opposite. It lets high frequencies pass through and eliminates low frequencies. So, for example, if you're taking an audio recording that's just like a recording of human speech with a bunch of background noise and whatnot, typically background noise tends to be lower in frequency than the people whose audio you're trying to focus on. So a low pass filter, or a high pass filter, can help preserve the people who are like the people in the foreground and eliminate background noise. And then a band pass filter is a combination of the two, where you zero out frequencies in the low and high ends, and you kind of focus on frequencies near the middle in some particular frequency range that you want. And the reason we do this is, of course, if you have some particular frequency range that you are trying to amplify, like for example, when you're mixing sound for, if you're mixing sound for example, a song or some other musical composition, you probably know in advance what instruments are involved and what frequencies they produce, and you can sort of fine-tune to boost those frequencies and eliminate non-instrumental noises.
Did you cover band pass?
I did.
Okay, great. All right, so we have some pre-recorded things that have. We already know what's coming, which makes this funnier in my opinion. So we're just gonna turn these off, and you get to hear Prem playing a scale on his phone. I don't know how well you will hear this, but I will hear it too well. But you can see the background noise. Can you hear it? You can see they're marching.
The ants go marching one by one.
Yeah.
You could probably get the idea.
Yes, okay, sure. Okay. Alright, and so we're gonna toss some filters on there now that were already made. Can we do one at a time? Or is it?
Yeah.
Okay, so we're gonna cut out that annoying background noise with this now, somewhat. But the problem is you can see that they're a lot lower now until they climb up. That's probably good enough. And now, if we do the opposite, we still get all that lovely background noise, because that's what we want, right? You can see it here.
And you straight up don't hear any of the high frequencies until they get higher.
Yeah, you see they are gone now. And then we can throw on both if you only want to hear the ones in the middle. Oh, that's so they're quiet. And I'm impatient. And I'm still impatient. So you can cut out just like this middle frequency in this way. What is this next one?
Play it.
Oh yeah, okay. I guess it's a mystery to us too. Okay. Oh. Yeah, I don't know what this is. It's two notes. But we can cut one out at a time. So let's see.
Do any of you musically inclined individuals know how to tell two notes apart that are being played at the same time?
Well, I hope
Yeah.
now you can. Yeah. And then
Yeah.
that high one is annoying, so we're gonna cut it out. And it's a lot less obvious.
Oh, it
And we
just
can
sounds
also
like a
do
C.
the other one to listen to this final. There you go.
Now it just sounds like an F with a little bit of C in there.
Yeah. And then the third one is bass boosting. A random clip of mine, because I had to think of something that wouldn't be copyrighted by YouTube when we upload this in like 2 weeks. I'm just
Uh,
kidding. No hate here. Okay, so we're gonna listen to it like a little bit without the filter. But I guess we're just gonna bass boost this one because I guess there is bass. And now, if you're still on the high pass filter, you can hear that the clapping is a lot more muted, right? So, and this is kind of like an inverse bass boost, I suppose, where you make the bass much louder in comparison to everything else. And then this last one, oh my god, I forgot what we said. Should we re-record this one? This is just us talking over a YouTube video playing in the background. But I guess we're about to find out what we said here.
Well, that's kind of insane.
It's-
1.2 million views
it's-
on 10 full hours of people talking.
Yeah.
I don't know who has time to watch 10 hours of people talking.
But if you think about it, someone could have made money off of this producing sound of people talking.
Can you imagine if someone copied for a video of people talking?
Could you imagine if someone transcribed this video of people talking?
That would be crazy.
Yeah. That is the last demo that we have. Unless someone would like to scream into my computer to make a new one.
This is an interactive portion.
Okay.
Benji, pull up.
Alright, pull up. Okay.
How loudly do you want me to yell?
Okay, it's working. Okay.
We're gonna make this interesting. Benji, scream into her microphone, and Claire will clap while you're doing that.
What? Okay. That's good enough.
Perfect.
Okay.
Easy.
Okay,
Alright.
I'm
Now.
fearful, so I'm gonna turn the volume down a little bit. But let's see. I need to open this again. Let's see what happens. Or we'll see at the frequencies. Unless I like manage to clap at the same frequency of Benji's voice, which would be an L, but we'll figure it out. Okay, so we're gonna try
So-
some of those.
So here's what's gonna happen. Someone in this audience is going to raise their hand and tell us, how do we filter out Benji screaming and only hear the clapping? What kind of filter do we use here? Sparsh.
High pass filter.
Hell yeah.
Okay, well let's try that.
Let's try it.
I have some doubts, but that's okay. But it's
I
not
mean,
because of the theory. It's
The
because
theory
of-
is sound, but theory will only take you so far.
Okay. Oh, yeah, there you go.
There you go. Nice.
Okay. Oh, my hands hurt. I clapped a little too hard. Okay,
But yes. Theory.
yes. Is that it for the demo?
I think
That's
that
it.
I
Okay.
think that's it. We can switch back to the slides now.
Excellent. Benji, I have your screen now. This is great.
I don't know what you're gonna do with that one.
I can.
Rude sandstorm.
I will.
Yo!
I will use it as a sample.
Go ahead. I give you.
Darude Sandstorm, but it's just Benji screaming for 5 minutes.
Okay, let's.
Anyway.
Oh no.
An autotune screaming sound would be crazy.
Earlier in the lab, we tried to find a video of Minecraft villager noises, but Darude Sandstorm. Anyway, this is all being recorded, by the way. I hope you guys know that.
It's okay, at least it doesn't have your faces. Okay, on to the math, because that's
Hell
what
yeah.
we're actually here for.
So, low pass filters, as we talked about, they eliminate high frequency components and let the low frequencies pass through. If you were curious as to how this works, this is the math for it. This is an equation. We're not going to explain how the equation works because that's not what we're here for. But basically, I mean, it's fairly straightforward. It's just, multiplication or convolution because this is the time domain. Continue. High pass filters, the exact opposite, eliminate the low frequencies and let the high frequencies pass through. This will eliminate things like ambient background noise and preserve, the higher frequency people talking foreground audio that we are typically looking for. If, for example, when we had Claire clapping in the foreground and Benji screaming was background noise. Anyway, bandpass filters will do both of those basically. It does the opposite of both of those. It blocks out both low and high frequencies and lets the stuff in the middle pass through. And as I said earlier, this is if you want to identify, for example, a very specific set of instruments in your audio that you're trying to, boost and filter out the stuff that's not those instruments. Sound engineers have to do this a lot when mixing sound for example, plays or movies. That is pretty much it. Thank you guys for listening.
Yes, thank you. Word.